Hello. I'd like to start with a statement that hopefully everybody in the audience is biased to agree with, which is computer vision is the future. So I'd like to explore a little bit what that future could look like. For us at Living Optics, that means computer vision that is everywhere and used for everything, able to solve existing automation problems in almost any setting, and enabling more informed decision-making across all aspects of our lives. So how do we go about making this future a reality? We do this by addressing the biggest limitations of computer vision today. In the next few slides, I hope to show you how Living Optics camera gets us one step closer to that future. So for any item to be used everywhere and used for everything, it has to be really, really useful. In computer vision, that is the automation of tasks. This is currently enabled by asking machines to extract information, visual information, from images that we capture about the world. Too many of these interpretations can fall over by everyday use cases. If we take the example of the image at the top of the screen, we see an apple and a sports ball. As soon as a hand comes in to grab it, the classifier has classed the apple as a sports ball incorrectly. It's confused by the context. Similarly, we have an example with ChatGPT trying to describe this image shown here. It thinks it's a crowd of people at a concert with large amounts of lights. It's actually combine harvesters going through a cotton field. It falls over. How do we address these confusers? Well, normally we throw vast data sets at them, but this is extremely costly and it takes a lot of time. So how can we perform better at these interpretations? Well, one way is to extract more information from what we're already looking at. Enter hyperspectral imaging. So conventional cameras to date, like the ones in your phone, use 3 color buckets: red, green, blue. And these are really good for taking pictures of holidays, your family, your pets. But for training machines, it's a bit of a legacy technology. We're limiting the information available to machines from the outset. Hyperspectral imaging takes the light and cuts it into many more color buckets. And this provides a much more detailed and rich description of objects around the world. This is far beyond what RGB can ever offer, and we call this description a spectral ID. At Living Optics, this is the information we believe we should be training machines on. With our visible near-infrared hyperspectral imaging camera, we can capture that unique description of objects that are beyond RGB and allowing you to distinguish it from other objects around it. What's more, this is done at video rate, so it can be used in the real world. And we have a friendly software stack that enables you to start augmenting your existing machine vision algorithms with this color information. Classification can be really difficult on objects that don't have shape. They're deformable or they're liquid. With the spectral information, it becomes a lot easier because you're just looking at the color of it and you're able to segment things that weren't previously possible. This is our camera. This is our development kit. We have a handheld camera that's up here. We also have the entire package included with the embedded compute, our software stack, our Python SDK, and a travel case that allows you to go out into the field, into the real world, and start collecting this data. We've tried to make it as friendly for developers as we possibly can to really lower that barrier into hyperspectral imaging. We want it out of the labs. We want it out of these factories. We want it out there in the world, people able to use it wherever they want to use it. We believe this is a step change for what machine vision can be capable of. So that's a really good marketing bit, but I really want to show you actually where we've been using our development kit in the real world and some of the unique capabilities that our camera can offer today with what we're able to solve. This will be a good showcase of how the hyperspectral imaging information complements existing machine vision algorithms. On to the main event, vineyards. So with climate change, we're seeing vineyard growers going further and further north, especially in the UK, where we're based. We have a rapidly growing wine industry there. Wine grape quality has a direct correlation with prices that can be charged for wine. So we've partnered with a local vineyard grower down the road from our headquarters. And he's a bit of a visionary. He has some really interesting, crazy ideas about getting people to adopt individual vines for their own personal wines that they want to create. And so he's looking for value on how to understand the health of his vines at a grape and leaf level, but make decisions at a vine scale. Here we have some of the spectral techniques that you can do. So on the left-hand side, we have the standard image of a leaf, RGB, standard machine vision cameras. And on the right-hand side, we start to see what some of the basic spectral techniques, such as NDVI and MCARI, can show you about the health of the vines and what's going on. We've taken a short video here. So this is our camera in action at the vineyard. We're showcasing the chlorophyll content here. It's quite a short video, so I'm just going to replay it again. It's not going to play. That's OK. This is a real-time footage. What you're seeing here with the leaves of the different color is the chlorophyll content, and that gives you an indication as to how healthy the plant is. We're collecting large data sets over this latest growing season, and we're starting to analyze those with more detailed spectral techniques, looking to correlate it with existing technologies such as Brix metrics, which tells you the ripeness of the grape, the sugar content, and things like that. We're also starting to look at how, using the leaves, you can see the water stress, heat stress, things like that, things that we're starting to see with more and more weather extremes that are happening around the globe. Specifically on the Brix metric, this is quite a slow and labor-intensive method for understanding the ripeness of the grape. It's also a very, very small sample size. So you get a refractometer, you pick a grape off the bit of the vine, you blend it together, and you look to see what solids and soluble sugars are present in there. With the Living Optics camera, we can provide a passive and real-time measure across your entire vineyard with up to 100% sample size. Eventually, we're hoping that these grapes get into some great wine and that we can all go and do some taste testing to really see the value of our camera. This is another slide. So on the left-hand side, we see another use of the data set. So within our camera, we have a standard RGB sensor alongside our hyperspectral data set. So you can leverage existing machine vision algorithms such as depth anything. And you can get some depth information using just the RGB sensor and really start looking at blending your existing data pipelines with this hyperspectral information. We've also got my colleague Dan here. I didn't ask his permission for this photo, so I apologize, Dan. He's living his dream, looking like a Ghostbuster here. And you can see our camera, our development kit, and he's walking up and down. This is an apple orchard here. But this is how easy it is for use for people. So, other unique capabilities that our camera is capable of. We're used to seeing results of deep learning and huge neural network machine learning techniques that have been made in recent years. It kind of shows with enough data, you can basically do anything you want, but there are still limitations. When you want to apply it to a particular problem, you generally have to augment data sets with thousands and thousands of frames and images that you want to solve for the problem that you're looking for. And this takes a long time. It takes a lot of cost. So one of the things that we believe our camera offers is that massive reduction in cost because we have that inherently more information at the outset. You don't need to provide it with as many frames. You can do it on a subset. Here is a video that's out of our HQ. We are just looking at the spectral information, and we've used the basic classifier to showcase some materials that are around. So we have our tarmac on the road, we have some artificial grass, we have some real grass, and we have some concrete slabs on the path. That video did not work. OK. all of these videos you can see at the end at the website livingoptics.com/demo. Unfortunately, they're not working here today. Locating anomalies. So because everything has a unique spectral fingerprint, we are able to isolate those individual spectra and use our software to track them based solely on their spectral angle metrics as they go around the world. What we have in this scene is we have one of my colleagues was a spectral tracker. He is walking along the street, and if the video plays, there we go, this one will play. What you can see here is our camera running about 30 frames per second. It's tracking him down the street using that spectra that we've isolated, and you can then reacquire as it goes away. No, it's not going to replay. That's a shame. What we can also do, based on that spectra, is that something that's quite unique is that if you get an object that hides the particular object that you're interested in, because we are on a pixel-pixel basis, you can still re-identify it as it's hidden behind and augment with segmentation-based algorithms. One of the interesting things that we're looking at is if you have multiple of our cameras, if you select and isolate a spectrum on one of them, you can hand that off to an additional camera and track a subject as it moves across a site or a system. So again, something that's quite unique with spectral information. Finally, we have another example of using our camera. On the left-hand side, we've benchmarked it against some existing YOLO models that are here. On the top axis, we have the accuracy improvements, the ability to uniquely identify an object and segment it. And on the bottom axis, we have our inference speed up, which is in orange. YOLO S is our benchmark. YOLO L, we see there's a degradation in how fast it can apply this, slight increase in accuracy. With our detector methods, so here we are just adding some spectral classifiers into a YOLO segmentation model. And you see here that because it's so lightweight, we are able to speed up drastically the inference and improve the accuracy. The segmentation is a little more involved. We put it through, take that spectral classifier again, you put it through a segmentation pipeline, optimize against it with some additional data, and then put it into a segment anything. This is an example that we've taken in our pear orchard. What you see here is this is using our LO segmenter. We have the green dots refer to the spectral sampling points that you have in the world. And then where the segment anything algorithm has determined it's a good enough cluster, it's then bounded that box. This has not been optimized. If we provided it with a lot more data, we would start to expect to see some of these pairs, which have been spectrally identified in the background as they've been hidden by leaves, would also get selected. So there's a lot of optimization to do, but I think it's a really good example of what our camera holds. That's a lot of information. This can be applied to so many applications. I chose the viticulture because it's one of our largest data sets. I know it's a problem that a lot of people are interested in. So I'd like to raise a glass to those, or a metaphorical glass, sorry, to our vineyard growers around the world. And if you're interested, please come and talk to our booth more. We have a live demo showcasing some oil segmentation based on the spectra alone. And as I said, there's a few more demonstration units across different applications that you can go and visit at that website. Thank you very much. That's all I have.
Thank you, David. That was a very nice application example of hyperspectral imaging.
Thank you.
Questions from the audience?
Stunned silence. I love it.
I don't see any questions, so maybe there's one. Do you still get visitors at your booth that ask hyperspectral imaging? What is that?
Yes, I think it's still a very new technology, and there's a lot of questions and education that's needed for to understand that there is all this extra information available in the world that, because we've been limiting ourselves with RGB to date, that we just haven't been aware is available to be used. So yeah, I think there's a lot of education to still be done. But there's been a lot of really interesting applications that are, as they've seen what we've been able to do, they've asked some really good questions and some left field things that we haven't thought of before.
So perfect, and I think application examples really help to understand what hyperspectral imaging can really do. And I wish you all the best and a lot of success.
Thank you.
In convincing more and more applications.